pulsar, where for the first time you see what people had theorized, that the wind of particles emanating from this pulsar would become shocked and start radiating in X-rays a distance from the object. And there's that ring, just like everybody thought it should be. And now you can study it in detail. From normal stars to comets to planets to active galaxies to supermassive black holes, to finding out that the hot gas in clusters of galaxies is not distributed nice and uniformly, that there's a lot of action going on, that those big active galaxies that are in clusters of galaxies and their supermassive black holes are doing all kinds of things on timescales of hundreds of millions of years. It sounds like a lot, certainly to me, but it's very short in the lifetime of a cluster.
We know that now in the centers of all galaxies that there's a supermassive black hole that has masses of up to a few billion solar masses. It's very compact, and at very early stages these were very active, and they corresponded to the quasars that are seen at very high redshift. But these supermassive black holes that were, formed at very early stages of the universe didn't go away. So they're still sitting there at the centers of the galaxies. So when you drop a little bit of material onto them, they give off X-ray emission primarily. Sometimes a bit of radio, sometimes a bit of infrared, but a fair amount of X-ray emission comes off.
Clusters are another area that are very active, and again, this was a surprise. We discovered a lot of structure in clusters of galaxies, which in the X-rays we had thought were pretty smooth, because mostly what we see is hot gas, and most clusters are very, very big, and it was imagined that they were in equilibrium and fairly smooth. But in fact, they found lots of structures of sort of like cold fronts that you get in the weather on the Earth. And Chandra is the only satellite that will be able to resolve those as well.
In the X-rays, what we actually see are regions around these black holes and these galaxies and these clusters. We see regions where the gas is carved out or pushed away, and we call them voids. They may not be totally empty, but the density of the gas is down by a large factor. And in those regions where the X-rays are deficient, where the gas voids exist, is the same regions where you see the radio lobes, these jets and lobes that are formed from the radio. So you know that energetic particles are being shot away from the black hole by some kind of mysterious process, and they're clearing the gas away. They're pushing the gas aside. Because the gas has a density and a temperature properties that we measure in the X-rays, it's very easy to calculate the amount of work that's needed to clear these voids. So you can actually measure the energy that's carried out by these jets of particles. You can measure the energy release. It's almost like a fossil record.
Well, Chandra is no doubt going to go down in history as one of the major astronomical missions that took us from very sort of rough descriptions of how the cosmos works and start to build up detailed pictures of what's really happening. Envisaged in the sort of 1960s originally, it was preceded by other X-ray missions, but missions which couldn't look in such detail as Chandra can. So Chandra is now taking all those sort of very vague ideas that we had about the way the X-ray universe was working and really giving us the physics behind it, rather than just sort of vague descriptions of how things might work. We're now starting to know how things work with Chandra. Chandra is essentially that link between the very vague, building up the physical understanding of what's really going on, and then going on from there to study things in much greater detail.
There's a very interesting Chandra result on a cluster of galaxies known as the Bullet Cluster. There's a small fragment of galaxies, a subcluster that's merging, and a shock has been formed, and it sort of looks like the edge of a bullet tearing through a fabric. We've seen that most of the mass is determined by the location of the X-ray emitting gas, and separately using Hubble and the Very Large Telescope and the Magellan Telescope on the ground, we've used a process called lensing to map the overall distribution of material by looking at the distortion and the shapes of galaxies on the far side of the cluster. Most of the material, namely the dark material, is located slightly in front of this X-ray gas that we see with Chandra.
Dark matter is important because most of the cluster mass, it turns out to be in the form of dark matter. So, and clusters are so big that the composition of clusters is exactly the same as that of the entire universe. So we can say if in these clusters of galaxies dark matter makes 70% of the total mass, we can extrapolate this result on the entire universe. If dark matter in the cluster makes 70% of the mass, it makes 70% of the mass in the entire universe.
So the reason why this matter has been dubbed dark matter is because, well, you know it's there. Just like you know the Earth is here. We are being attracted by the center of the Earth. Just like you don't see the Earth from this room, you are unable to see what is the matter in a galaxy which causes this attraction. Still has to be there. The only alternative is that Newton's laws of gravitation are wrong, and most people would question that statement. So, is there? You measure the gravitational attraction, you just don't see it. So, I guess the obvious name for this type of matter is, well, dark matter.
From the obvious but invisible influence of dark matter to dramatically visible supernova remnants, Chandra continues to astound us.
The thing about supernova remnants is that they're big objects. They're the result of massive star explosions that have blown the insides of the stars completely out into space. And there's a process of nucleosynthesis that goes on during those explosions that synthesizes heavy elements all the way up, all of the heavy elements that make up the interesting things for us, the carbon and oxygen and iron and the things that allow us to be people.
You know, every kind of object that you can think of in the universe, there has been a representative of that class of object has been seen in X-rays with Chandra and even with missions before Chandra. And so there's a lot to study, the whole range of questions from the solar system, you know, out to objects in our galaxy, whether they're normal stars like similar to our sun or the endpoints of stellar evolution like neutron stars, white dwarfs, or black holes.
Chandra's X-ray images continue to add volumes to humankind's understanding of some of the most fundamental processes of our universe.
The biggest and most important scientific contribution that Chandra has made is to give us an X-ray tool on a par with any other wavelength range to study the universe.
I think it's well understood at NASA headquarters and indeed all through the scientific community how special Chandra is. It's really the gold standard for X-ray astronomy right now.
It may be that we're at a particularly special point in time where these key discoveries are made, and once we understand them, we've made certain incredible breakthroughs of our understanding of the universe and the laws of physics that govern the universe. And it's possible that in 50 or 100 years people will look back and think about how crude our telescopes were and how limited our ideas of the universe were. We don't know at this point. One could imagine that our imaginations are inadequate and that the discoveries that are still to be made are just unbelievable.